The U? Same molecule? Or different?
Same.
What's their relationship? Enantiomers. What do you notice between the two of them that makes you think they're enantiomers? Okay, but I told you everything has a mirror image. So what else has to be true about these mirror images? They cannot be superimposed. Look at when I try to get the yellow group to line up. The methyl group, this little CH3, lines up, but my red group doesn't. So let me try to make my red group line up. It can't line up without displacing the yellow group. Now, there's this interesting thing that happens. Molecules don't really just break their bonds very easily, but should I be able to rearrange just two of the bonds connected to this carbon, look what happens. Now I can superimpose the molecules. But are they mirror images? No, the red groups don't mirror each other anymore. Or I can get the red groups to mirror, but the yellow groups will not. These are identical. That's their relationship, and they are not mirror images. But again, I'll swap any two groups, and this time, I don't know if you guys saw it, but last time I swapped the red and the yellow group. This time I'll swap two groups, the hydrogen and the methyl. And look what I've gotten back to. Mirror images that cannot be superimposed. So we're describing relationships between two molecules when we describe them as being identical or when we describe them as being enantiomers. There is another type of stereoisomer after enantiomers, and these are called diastereomers. This idea of, you hear stereomer in there again, so you understand we're talking about stereoisomers. But this idea of dia at the front, diastereomers, I like to have it make me think of two things. This is a relationship between molecules that are not mirror images. But they still have the same chemical formula and the same structural connections. They are not structural isomers because structural isomers have different structural connectivities. They are connected in exactly the same way. They take up space differently, but unlike stereoisomers, enantiomers, which take up space exactly the same but mirror imaged, these take up space not in a mirror image fashion, and they still cannot be superimposed. In order to dive into this a little bit better, we need to take a step back and start looking at some descriptors. So we're moving now from relationships between molecules to descriptors. I shouldn't move yet, should I? I should put some examples up on the board. It's best to do this with a molecule like this. Cis 1,2 dimethyl cyclohexane. Cis 1,2 dimethyl cyclohexane has no enantiomer. Its mirror image is superimposable on itself. I can actually prove that by drawing the mirror image of cis 1,2 dimethyl hexane, cyclohexane. And then look what I can do. Just rotate it 180 degrees and slide it over, and it perfectly superimposes. So that is its mirror image, and it is superimposable with its mirror image, which means these two structures are not enantiomers. They're identical. So what would be a diastereomer for cis 1,2-dimethyl cyclohexane? Well, it needs to be connected in all the same ways. So it needs to still be 1,2-dimethyl cyclohexane. But it can't be a mirror image of it. So I'll take one of those methyl groups, and I'll change it from being a wedge to a dash. These two structures are connected in all of the same way, but they are not arranged in space the same. They are not mirror images. Otherwise, maybe both of these groups would be dashed. They are not mirror images, and they cannot be superimposed, but they are connected in all of the same ways. Alex.
So does this have overlap with like the cis and trans isomers then?
You agree that these are cis and trans, right?
Yeah.
Here's cis, here's trans. Turns out that cis, this cis isomer has no enantiomer, but this trans isomer does have an enantiomer. You're right, there is overlap and distinction. Cis-trans isomers are a type of diastereomer. In fact, we were looking at stereoisomers. You're right, I kind of forgot. The first one we looked at was cis-trans. Then we looked at enantiomers. And diastereomers are a different perspective on cis-trans isomers. Here's how I want to say that. All cis-trans isomers are diastereomers, but not all diastereomers are cis-trans isomers. That's a good, I love that little rectangles and squares thing that I learned in high school, and I never let go of it. Okay, in order to understand these better and to be able to predict trends better, I want us to start talking about chiral centers. Chiral is a Latin word. Do you guys know what it means? It does not mean circular. Aaron, I missed what you said.
Oh, I said spiral.
It does not mean spiral. Chiral. What does chiral mean? I gave it away. No, not 5. No, good try.
I don't know what you're doing.
Yeah. Hands. Chiral is Latin for handedness, hand stuff. And it's because your hands are a great example. The reason that we pulled that Latin word for hand and brought it into chemistry is because your hands are a great example of things that are asymmetric. Chiral centers are also called asymmetric centers, or specifically, we're going to be looking at carbons, so we'll say asymmetric carbons. We're going to also put A in front of chiral, so we're going to create a vocab word, achiral, which means symmetric. So chirality is asymmetry, and it is such an important concept in chemistry that we gave it its own word. Rather than just calling it asymmetry, we call it chirality. A chiral center is defined as having 4 distinct groups. Notice it's not 4 distinct atoms that it's bonded to, but 4 distinct groups. And as a result, it has no internal plane of symmetry. So we could start small Let's look at bromochlorofluoromethane. That's a weird thing. Don't make me say it more than once. That is a chiral center. It's bonded to 4 distinct atoms, 4 distinct groups. There is no plane of symmetry. This can arrange itself one way in space, and it can arrange itself another way in space, and they are not the same. They are distinct from each other. This has an enantiomer. Let's look at a bigger molecule. This is 2-butanol. How many chiral centers does 2-butanol have? This CH3 group is achiral. It is not bonded to 4 distinct groups. It has 3 hydrogens that it's bonded to. This CH2 and this other CH3, also achiral. The CH2 has 2 hydrogens, achiral. Then I look at this carbon here, my second carbon. This carbon is bonded to a methyl group, an ethyl group, a hydrogen, and an alcohol. Those are 4 distinct groups, even though the first atom in 2 of the groups is identical, carbon to carbon, carbon to carbon. What we need to look for is a difference in the group. Any first point of difference. Carbon and carbon is the same, but the only other bond here is hydrogen, and this group here has another bond to carbon. So there is a distinction between those groups. I could even try to highlight that distinction. Here I'm just showing my chiral carbon, and I'm going to kind of map out my other groups. I have an oxygen, a hydrogen, a carbon, and a carbon. Notice that I'm not even putting OH. O is enough for me to know it's a distinct group on its own. But carbon and carbon are not distinct. So I continue down this group. There's a bond to H. Continue down the group on the right. There's also a bond to H, but let's look for the difference. There's also a bond to C. Not a point of difference, is a point of difference. Let's take another look. How many chiral centers in this structure? I hear 2, another 2. Anybody else? Anybody thinking 3? Let's go through and prove. Is it fair for me to rule out all of my CH2 groups? We already said that if it's attached to 2 hydrogens, those 2 hydrogens will be symmetric to each other, and that carbon will have an internal plane of symmetry, and it will be symmetric, which makes it achiral. Achiral, achiral, achiral. What about this carbon? It's bonded to a hydrogen, that's assumed. It's bonded to a methyl group. It's bonded to a CH2 in the ring, and it's bonded to a CH in the ring. Those are all different groups, despite the fact that 3 of them involve carbon. That's a chiral center, 4 distinct groups. What about the carbon above it? It's in a very similar environment. A hydrogen, a methyl, a CH in the ring, and a CCl2 in the ring. 4 distinct groups. That's a chiral center. What about this carbon here? It's bonded to a CH2 in the ring, and it's bonded to a CH in the ring. Those are distinct, but it's bonded to 2 chlorines. Might as well be 2 hydrogens. 2 groups that are the same, they can be reflected into each other by a plane of symmetry. No chirality. Chirality means lack of symmetry, just like your hand has lack of symmetry. This is not a chiral carbon because it has two identical groups bonded to it.
Can you go over what you were doing with this bottom middle one?
Here?
Are we saying this is or is not chiral?
This is a chiral center.
And are we representing that same one right there?
It is that dot, yep.
So when you crossed out the C's,
That's not a point of difference between these groups. So I'll say this. The oxygen is different from the carbon and hydrogen groups.
so this is chiral.
That's right.
Okay,
This is a chiral center.
okay.
4 carbons, one of them is chiral.
So you can just like keep going with the bonds
As
until you
far as you need to go.
Okay, until you find it different.
Absolutely. Let's take some alternative perspectives.
So those two that are attached to the methyl groups, they're chiral carbons, and is chiral carbon like synonymous with chiral center?
Mm-hmm. Yeah, so you can swap this a lot. Chiral carbon, chiral center, chirality center, asymmetric carbon, asymmetric center.
Even though it's not in the center of the molecule.
That's a great question, or a great perspective. You guys know in Gen Chem we talk about molecular geometry, and how many atoms do you apply molecular geometry to? 1. You look at one center atom and you describe its molecular geometry, which means that a molecule can have a dozen molecular geometries. It's not a good fit. So I hear what you're saying. It's not the center of the molecule.
But if I zoom in,
It is a center point.
Gotcha.
It's a central atom. Good perspective. All right. I want to take some alternative perspectives on our molecules and see if we can find chiral centers. We talked about these Fisher projections. These are often used to describe sugar molecules. So this is just a straight line, CH3 at the top, CH2OH on the bottom, and then 3 horizontal lines, H on the left, OH, H on the left, OH, OH on the left, H. We're not diving in too deep with Fisher projections. Remember that there is an assumed perspective here. We have assumed to take this carbon chain and create it into a linear backbone. It's a highly energetic conformation. It's not a stable conformation. And then we look at it down this backbone. This guy will cooperate. So we've got an assumed perspective that there are groups coming at us and that this backbone is bending away from us. I'm sorry that it's not working better. But we're not diving in too deep with that assumed perspective. All we need to know is that there is stereochemistry here. Are there any achiral centers in this molecule? Give me one. The CH3 is achiral. What else? I didn't really point that out here, by the way. These CH3s are achiral as well. What else is achiral? CH2OH. It's got 2 hydrogens. All right. Well, what about this guy up here? Is that a chiral center? It's bonded to a CH3. It's bonded to an H, an O, and then it's bonded to the whole rest of the molecule. Chiral center. Next one down. This one's got a hydrogen and an OH. Up top, it's got a CHOH, and beneath it, it's got a CHOH. Those are the same group.
But they're attached.
Good. Maddie's got it. Keep going. Past this is a CH3. Past this is a CH2OH. Russ, you got a good point that the H's and OH's are attached differently here. But this carbon doesn't really know how the other carbons are attached. All it sees are what atoms are there. Are they distinct on either side or are they not? These are the same. Here to here. But then I have CH3 and I have CH2OH. That's a point of difference. That's a chiral carbon. What about my last one? Chiral carbon. Let's look at this chair conformation. Can you name that molecule by its chair conformation? If I swap those methyl groups with chlorines, could you still name it? What's its name?
1,4-dimethyl cyclohexane.
Close. Minus 1/4 point. Trans 1,4-dimethyl cyclohexane. Because I know their stereochemistry. One is a wedged group, one is a dashed group. One is up equatorial, one is down equatorial. Is this its lowest energy conformation or its highest energy conformation? The other conformation, both of those groups will be axial and it will be much higher. Are there any chiral centers in this molecule? This carbon and this carbon is probably where your attention is being drawn. And if you go around the ring, you get CH2 on both sides, CH2 on both sides, and then you meet back up on the other side. There is no point of difference, which means that those carbons have an internal plane of symmetry. We could actually try to sketch it. It looks like this. It kind of cuts, through the ring here. Yeah, I said we could try to draw it, but it doesn't mean it's going to look good. It might be easier to show it by converting it from its chair conformation to its bond line conformation, its top-down view. I can see that there is a plane of symmetry in that molecule. That plane of symmetry cuts through those two carbons. Those carbons have a plane of symmetry. They cannot be chiral. They must be achiral. In fact, we can do that with pretty much any chair conformation or any top-down view of a ring. If you can draw a plane of symmetry through some things, then they are not chiral. Let's look at a Newman projection.
You would never say that a molecule itself is chiral.
We will.
Oh,
Yep.
okay.
Yep.
So for right now, is carbon chiral?
That's right. We're just looking at chiral centers. We're going to see how that expands to the molecule next.
Okay.
Good question.
You know, I already said this, but like, so like if there's a central carbon that's bonded to a carbon, does that count as a distinct group?
You want to look at every carbon.
Mm-hmm. I was like in this one right here. Like
Yeah.
the front carbon is connected with a hydrogen. You could say oxygen, and then the top carbon, would that be?
That's only three
Oh,
groups,
it's
though.
three. Yeah.
Where is the fourth group?
Behind.
The other carbon
Yeah,
behind
okay.
it. Yep. If it's easier to convert this into bond line structure, do it. It's really good to have that skill of being able to convert both ways. How many carbons in this molecule? 1, 2, 3. 3 carbons. How many of them are absolutely achiral? Definitely the methyl group. Methyl group, never going to be chiral. This front carbon is bonded to the carbon in the back, bonded to the carbon up here, bonded to H and OH. So definitely 2 distinct groups. But is the CH3 group the same as my back group? No, the back group is a CH2OH. So that's 4 distinct groups. CH3, CH2OH, H, and OH. That's a chiral carbon. My poor marker. And what about the circle? The carbon in the back. Why is it achiral? 2 hydrogens. Those hydrogens will be able to reflect into each other. Let's look at this bond line structure. I'm gonna try to draw it in a way that you could model it. It's not gonna be perfect, but it looks something like this. And now it's a little bit easier to see. Achiral, achiral, chiral. That center carbon has 4 different things going on. All right, now I want to look at just one more for you. The distinction with this molecule is that it's actually closer to what we normally draw throughout the semester. It's not a Fisher projection, it's not a chair conformation, it's not a Newman projection. Those are all things that help us understand the molecules in different ways. But this just looks like a perspective drawing. I've got a wedge group and a dash group. And a lot of the times, chiral centers can hide. They don't have to have these wedges and dashes. You just need to know that it has 4 distinct groups. But it's really important to know how those chiral centers are arranged. And so you'll often see those chiral centers with wedges and dashes. But not everything that's shown with a wedge and a dash is a chiral center.
So if you were, like, let's say you're a central carbon, you have 2 methyls on both sides, could you just do a CH from one and a CH2, or a CH from one and then just an H from the other?
To make them different groups? No, what I would say is if you are a central carbon and you have 2 CH2 groups, those are 2 identical groups. They might as well be hydrogens.
Oh, okay, so you can't really, like, pick it apart.
You can't. Because what you're trying to do is find the first point of difference, and you cannot find a point of difference between a methyl and a methyl.
I think I just got confused, because there's 2 carbons there, but we just kind of...
But one is a methyl,
Right.
one is an ethyl.
Oh.
So this carbon chain stopped, but this carbon chain kept going.
Oh, I see.
And I could, you know, with this example, I could elaborate further. I could show all of the groups that are bonded there. But the point of difference is this hydrogen versus this carbon. That's where the two groups distinguish themselves. How many chiral centers in this 2-methyl-3-pentanol? 1 chiral center? We can agree that none of the methyl groups are chiral. We can agree that the CH2 group is achiral. So my attention is drawn to these 2 carbons that have the stereochemistry, the wedge and the dash. Is this carbon bonded to 4 distinct groups? It's got OH, H, CH2, CH. That's 4 distinct groups. That's a chiral center. Did anybody disagree with that? I'd like to hear what made you think otherwise. Okay. Now what about this one? It's bonded to H, CH3, CH3. Oh, already achiral. 2 methyl groups doesn't make it chiral. This is a tetrahedral carbon, so it does have a wedged group. But it's not a chiral carbon. It has an internal plane of symmetry. Okay. Before we start applying these terms, chiral and achiral, to larger molecules, I want to look at this definition called absolute configuration. Chiral meant what again? Asymmetric. And it comes from what Latin word? Yeah, I said that a little wrong. It comes from the Latin word for hand. So, this is how I like to demonstrate this. What hand is that? Why is it my left hand? Because of the thumb, right? So if I do this, it fits still. So it's not the thumb.
It'd be the thumb in relation to the palm.
Oh, nailed it. You've got to have a reference point in order to know absolute configuration. Your hands are enantiomers of each other. Your hands are chiral, thus taking the Latin word for hand to describe asymmetric things. But that doesn't mean that you can easily tell which hand you have. It goes the same with chiral centers. They can be arranged in 2 different ways. They can be non-superimposable mirror images of that chiral center. That's what I was demonstrating with you guys before. One chiral center with non-superimposable arrangements in space. So how do you know which one you're looking at when you do have stereochemistry? When it's explicitly shown as a wedged or a dashed? How do you know? This, where it's flat, a flat chiral center, that would be similar to this. Or let me show this with butanol. But now if I redraw this, and I make that alcohol a wedge, it is distinct. It's a different molecule than if that alcohol was dashed. They take up space equal but opposite. So this drawing of the hand isn't distinct enough. I need a way to recognize which hand it is. And we can do this when we're drawing things. For instance, I could put fingernails on the hand, or I could draw in the knuckles. And now I know palm is away from me. I'm looking at the left hand. We need to do something similar when it comes to this wedged group. We need a way to describe which one it is, and we need a way to reference the molecule consistently so that we all name the molecule the same way. So we're going to call the absolute configurations R and S. These are just the terms that we'll give to it. They also come from Latin for like basically good and bad. I forget right all the time, but S is sinister. It does mean good and bad, but it also means right and left. I don't know if you guys know that, but across cultures, left is associated with bad. Oh, gauche is actually French for left, but I told you guys that gauche was French for awkward, but that kind of derived from gauche meaning left. That is an awkward thing. That's not a better thing. Sinister is left. Whatever R stands for is right. And there's actually a way that I'm going to help you guys remember this. We're going to identify the 4 groups that are attached. And then we're going to find rotation between those 4 groups. And if the rotation is right-handed, clockwise, then we'll call it R. So notice that I've got this rotation arrow, and it makes up the top of the R. If the rotation is counterclockwise, left-handed, then my arrow makes up the top of the S, counterclockwise. Rather than giving this a name, like the absolute configuration priority name, they called it after the 3 scientists that worked it out and developed it. So the Kahn-Ingold Prelog rules. Their first rule says prioritize the 4 groups. From highest to lowest atomic mass at first point of difference. What's the highest atomic mass from my chiral center in 2-butanol? Oxygen. My lowest atomic mass to my central carbon. Hydrogen. So I'm going to sketch that in. That's a dashed hydrogen. That's priority group number 4. What about the methyl group to the ethyl group? What's a higher priority? Yeah, we're looking at the first point of difference. And remember, we said that was the second carbon of the ethyl chain versus the hydrogen of the methyl chain. So this gets priority 2, this gets priority 3. I want to give you guys a tip here with rule number 1. Quaternary carbons are higher priority than secondary carbon, than tertiary carbons, than secondary, than primary carbons. So what we were doing here in deciding the priority difference between ethyl and methyl, we were really just looking at a secondary carbon versus a primary carbon. And the idea is the more substituted the carbon, the less hydrogens it's going to have. And so it will beat out a less substituted carbon at some point by having more carbon to hydrogens. Secondary carbon, higher priority than primary carbon. There is another tip that comes here, which is multiple bonds. count multiple times. I'm going to have to give us a different molecule to demonstrate this. But it will be worth it. This molecule has one chiral center. Oh, no, it doesn't. I'm sorry. I've added an OH group to that central carbon. Now it has one chiral center. That was my mistake. I had a CH2 group and 2 hydrogens. They'll give a mirror plane. This is achiral, CH3. This is achiral. It's not even bonded to 4 things. It's bonded to 3 things. Can't be a chiral center. And this is achiral because it has a CH2. So this is my chiral center. What's the first priority group? It's bonded to oxygen, carbon, carbon, and hydrogen. Oxygen takes first priority. Hydrogen takes last priority. Hydrogen takes fourth. And then I've got carbon, carbon. No point of difference. Then I've got a bond to oxygen, and then I've got a bond to oxygen. No point of difference. But then I've got a second bond to carbon, all right, oxygen, and here I run out and I only have a bond to hydrogen. So the carbon is not a point of difference. The bond to oxygen is not a point of difference. But the second bond to oxygen versus a bond to hydrogen is a point of difference. Yeah? Multiple bonds count multiple times. I was able to count this carbon's bond to oxygen twice because it is 2 bonds. And it canceled with this bond to oxygen once, but then I got to use it again. All right, you guys okay with that idea? It really just comes down to situation. But when you run into the same atom in 2 directions, but one of them has multiple bonds, you get to count it multiple times.
So when we're saying we're prioritizing based on the atomic mass, it's not about how big that branch might be.
No.
It's about how the atomic mass of which one we are counting.
This group could go on to infinity, and it would have the mass of the universe. And this group would still take higher priority.
Because of the double bonds.
Because we're dealing at the first point of difference. These 3 scientists could have said, listen, let's set our reference to say, organize the 4 groups by their mass, by the mass of the group. We would run into some issues when we had cyclic structures, because like, when do you stop counting the group? How many times do you go around? And if we had a huge molecule, it would take so long to add up the mass of those groups and to figure it out. So they gave us a shortcut, and they said, if we consistently just prioritize the groups at the first point of difference, we usually don't have to work that hard to prioritize them. It means nothing. It's just a way to systemize our absolute configurations. Okay. Rule number 2. With priority group 4 placed backwards, which means dashed, determine rotation clockwise or counterclockwise for groups 1 to 2 to 3. Which means do not consider priority group 4 in your rotation. Now this is the reference point. This is saying The direction from thumb to pinky is counterclockwise on your left hand when your palm faces away. And your direction from thumb to pinky is clockwise when your thumb points away. So we have to have that reference point, otherwise it doesn't work. So we've already prioritized 1 to 2 to 3. My rotation is clockwise, which means my chiral center has an R absolute configuration. We could have said it has a left-hand configuration. We could have said it has a right-hand configuration. We could say that it has a zebra configuration, a muscle configuration, but we've just said that it has an R configuration. We understand what R means based on these rules. If that priority group is forward, meaning that it is wedged, then you assign rotation opposite of what it appears. If your perspective is backwards, then you just assign backwards. What direction do the hands on a clock move? Clockwise. Have you ever asked the numbers on the clock what direction the hands move? Set yourself at those numbers. I'm the number 12, and I'm watching the hands move. My hand, to me, is moving counterclockwise, and I'll prove it. You guys see it? It's moving counterclockwise relative to the numbers, clockwise to us. If I could step behind the plane of the board and look at this arrow, my arrow would look like it is not going clockwise, but it's going counterclockwise. So if your perspective is wrong, then you just assign it opposite. I'm telling you that my thumb to pinky clockwise is my left hand if my palm is going forward or away from me. But if my palm is going forward, thumb to pinky is counterclockwise for my left hand. So you have to determine the rotation, assign it opposite. Let's look at that. Let's apply it. I've changed from a wedged OH group. Now I have a dashed OH group. Would you agree that the priority groups do not change? Where is my fourth priority group? It's coming out towards you. It's breaking rule number 2. So I assign the rotation, I determine the rotation to be clockwise, but I think you guys can agree the position of my H and OH have swapped here. Just like I showed you before, those two bonds are now connected by swapping them. These can't be the same absolute configuration. They can't be the same molecule. So why is the rotation going the same way? It looks like it's R. But we've broken a rule, and it's actually S. Now you could go through the work of placing the fourth priority in the back. So take this molecule and flip it like a pancake. This dashed OH group, as it flips, is going to become wedged. It's going to be coming towards you now, but it's going to be on the other side of the molecule. Left and right have swapped, front and back have swapped, because all I've done is spun it around. And now you can see this is the same molecule, but I'm actually following the rules, and the rotation from 1 to 2 to 3 is S. This is important because when you take Vicks Vapor Rub and you put it on your chest or next to your nose, helps you breathe better, that is one absolute configuration of a molecule. The other absolute configuration of the molecule is the addictive methamphetamine. So you just change the position of one methyl group in space and your nose opens up versus you get addicted to meth. How important do you think it is that Vicks Vapor Rub gets the right absolute configuration in their products? Very important. This also applies with a lot of medications. So there's antidepressants that have this chiral center. And for some of them, one absolute configuration, one enantiomer, works as an antidepressant, and the other one has no biological side effects. So they can just make both versions and put it in the pill, and it's going to be fine. But some medications have a positive effect with one absolute configuration and a detrimental effect with the other. There's a birth control, or no, a pregnancy nausea medication. It miles nausea during pregnancy. If you change the absolute configuration of its chiral center, it causes birth defects. There's a natural plant, or a natural product produced by plants that can cure some types of cancer. But if you change the chiral center's configuration, it causes cancer. So the arrangement in space is very important. And I think you guys would agree as well with your hands, the arrangement in space is important. If somebody sold you a pair of gloves and there were 2 left-handed gloves, you would want your money back, right? Because your hand cannot go into a left-handed, your right hand can't go in a left-handed glove. It's not going to work. There's no benefit. But sometimes there are detrimental effects. You had a question?
Yeah, can our bodies change the composition of it and like make it a chiral center configuration to have those defects you're mentioning?
Well, that's an interesting thing, and it gets more into biochemistry. Enzymes can do some wild things. Enzymes can take achiral centers and make them chiral, or chiral centers to achiral centers. I don't know if I've ever heard of an enzyme that takes one absolute configuration and changes it. But I wouldn't be surprised. They can do some wild things. Maddie?
So how would you make one or the other?
Well, synthesis is another beast. There are actually, we call them enantiomer specific reagents. They are chiral reagents of their own. So they kind of promote reactivity on one configuration and inhibit reactivity for the other, which is similar to how enzymes work. Your enzymes are enantiomer specific. They care about the stereochemistry. But we're not going to get into it much, actually. Okay, I want us to be able to go backwards, too. So here's what I want us to do. I want us to show 1R, 2R, 1,2-dichloro cyclopentane. Do you see how the absolute configuration of the chiral carbons has been specified in the name before the prefix? So nomenclature can now accept stereochemistry indicators. Yesterday, we would have actually called this molecule trans 1,2-dichlorocyclopentane, but there are 2 trans molecules, and they're enantiomers of each other. So we're going to be drawing a specific enantiomer. Cyclopentane, 5-membered ring. 2 chlorine groups at positions 1 and 2. Okay, am I done? You don't know that those are our absolute configurations? Why not? There's not enough information. I don't know which group is forward, and I don't know which group is back. It's not that it's neither R or S. Those are chiral centers, so they are either R or S, but I don't know if they are R or S. But I can still do group 1, or step 1. So I'm going to focus on this carbon. Its priority groups go 1. Then I look at 2 carbons. I have to look past them. I'm comparing chlorine to carbon. Chlorine wins as the highest priority group, and then this other carbon group. And my last priority is H, the H connected to my chiral carbon. We could do this by just a method of guess and check. If my chlorine was wedged, and I'm following rule 2, then my rotation would be 1 to 2 to 3 clockwise, which would give me 1R. So I'm happy with that. I want this to be wedged. And did that have to be position 1? You guys agree that this could have been position 1 as well, right? The nice thing is that position 2 was also R. So that was always going to work out. You guys okay with this? I determined the groups, and then I said, if priority 4 is back, this gives me a clockwise rotation, and a clockwise rotation is R. Now, let's do it again for the second one. And just for sake of clarity, I'm going to redraw it with the information that I already know. Priority group 1 on this carbon, still the chlorine. Priority group 2 on this carbon, still the CHCl. Priority group 3, still the CH2. You'll notice that the only difference is how priority groups 2 and 3 are placed relative to the chiral carbon. But this first chiral carbon had all of the same groups that this chiral carbon has. And now I look at rotation from 1 to 2 to 3, and how does it look? It looks S. So if this chlorine is wedged, do I have an R configuration? If that chlorine is wedged, I have an S configuration. And am I going for S? So how do I make that chiral center R? Make the chlorine dashed. Because now it looks like it's S. But if I looked at it from the other direction, this rotation from the correct perspective is clockwise, is R. So it looks S, but we're using that tip after rule 2. What do you guys think? A little guess and check.
Is that for only if you were to sign, like you were to swap it and you assigned like the dash chlorine first? Because is the left one wrong?
This one?
Left one. I meant like the left drawing.
This is wrong because this chiral center is not R or S. It's a chiral center, but there's not enough information about its stereochemistry. I don't know if this chlorine is wedged or dashed, and that impacts whether that chiral center is R or S. You know what I mean? We started by drawing it as just this, which can only be described as 1,2-dichlorocyclopentane. And then we fixed this chiral carbon, so now we can be positive it's 1R, 1,2-dichlorocyclopentane. But then we had to fix this chiral carbon to make it 1R, 2R, 1,2-dichlorocyclopentane. So we kind of took it one step at a time. What stereochemistry do I need here to make that chiral center R? What stereochemistry do I need here to make that chiral center R? And we can do guess and check. Give it a wedge. Is it the configuration you want? No. Make it a dash. Now it will be the configuration you want.
So it wouldn't have changed anything if you picked the other CL to start with?
Would have changed nothing.
We would have just determined that it was dashed.
You would have started by finding out it was dashed.
Okay.
And then we would have done the carbon on the left, and we still would have found out that it was wedged. So what changes when the name becomes 1R, 2S? It becomes cis 1,2-dichlorocyclopentane. Both groups are wedged or dashed. There would be no difference. Okay, what do you guys think? It's possible to go forward and backwards. You just have to do a little game of guess and check.
So just to piggyback on what Aaron was saying, if we started with the wedge, the reason we'd end up with the with the dash on that second one is because we would still end up with the same priority.
The priorities are the same, organized in the same direction.
So the priority dictates the order, which dictates the rotation,
Yeah,
and that dictates R versus S.
that's right.
Okay.
Well, priority dictates the rotation. The placement of the lowest priority group dictates R versus S.
Right.
There's another thing I'm doing here, which is intentionally leaving out the possibility of the lowest priority group being in plane. You cannot assign R versus S if the lowest priority is in plane. It is impossible. So you have to then take a Newman projection on it, rotate it, put it back into bond line, and then assess it. You have to have the lowest priority front or back. One of the tips I do give otherwise is, let's say in this example, like my lowest priority was here in plane. I could actually say, this is priority 4, this is priority 1. I'm going to swap those priority groups. I'm going to call this 1, I'm going to call that 4. And then I will assign the rotation because now 4 is forward or backwards. But anytime you take two bonds and you swap them, you've changed the absolute configuration. So then you have to assign it using your rules and then know that you changed this chiral center and flip it back. I don't give it as an option ever, because to me it's just too much work. If you can do this, you're doing well. If you need to do that, you'll do it if you can do this. Someone had a question?
I did. I'm just kind of stuck on like the dashes and the wedges and how you like flipping the rotation.
Well, look at the clock.
Well, yeah, I understood that reference, but so with like the drawing that you have on the left, because you labeled it 1, 2, 3, because that was how it was prioritized.
Yep.
But then.
And they were connected by rotation 1 to 2 to 3 clockwise.
Yeah, and then.
And rotation 1 to 2 to 3 is an R configuration.
Yeah, 1 to 2.
If and only if the fourth priority group is back. and the priority group is back because I made this wedge. The fourth priority group, sorry. Fourth priority group is back because I made.
Oh, because the chlorine's in front. Is that what you're saying? Okay, that was like what was throwing me off. Was
We are assuming the hydrogen, and we are assuming that the hydrogen is dashed because I already have the two in-plane lines if I touch with equal center, and I have the wedge. The only position left is the dashed group.
okay.
So there's no way you could actually just look at the 1R, 2R and be like, oh, there's two R's, it's translucent. You'd have to like
Yes.
actually go through?
You can.
Okay.
You can decide that. It's harder though. And I would say just takes a little bit more practice. Actually, one thing that you can say on a ring, this is not always true on linear chains. On a ring, if you have RR, they will be trans. If you have SS, they will be trans. But you would actually have to go through and decide which one is wedged, which one is dashed. And if they are RS, they're cis. And then it actually doesn't matter which way you do it.
And that's any size ring?
Yeah. Mm-hmm.
So basically, I'm just trying to figure out, so like the takeaway from this is just like the nomenclature naming aspect, and R just means to the right and S means to the left, and the numbers are where it's at.
R means clockwise connection between 1 to 2 to 3
Right, depending on the
when lowest priority is back. S means counterclockwise connection between 1 to 2 to 3 when lowest priority is back.
and if they're the same like structure, it doesn't matter if you go wedge or dashed, just whichever one.
I mean, it does. Oh, it doesn't matter if you started with this carbon or started with this
Right.
carbon. Yeah. So when you're building it from a name, you can just start wherever you want. Each chiral center is only going to be correct one way, independent of the other chiral centers. Actually, we have that Fisher projection with the alcohols. And I think you said, oh, the OH is relative to that central carbon. No, was it not you? The two OHs are arranged differently, which was a really good thought. Those were all chiral centers, but the central chiral center doesn't care what the chirality at the other chiral centers is. It has its own chirality. That's all it worries about. Okay, I want to take this back to our discussion on relationships. We can easily spot enantiomers by noticing that all of the chiral centers have flipped. Some students would look at this and say, well, the chiral centers haven't flipped. I still have one wedged chlorine and one dashed chlorine. Okay, well, priority 1, 2, 3, connected via a counterclockwise rotation. That's an S priority. And then 1, 2, 3, connected via a wrong clockwise rotation, because priority 4 is forward. That's an S configuration. This molecule was 1R, 2R. This molecule is 1S, 2S. 1S, 2A. All of the chiral centers are arranged differently in space. It's, you know that saying, he dances like he's got 2 left feet? His enantiomer has 2 right feet. They might be just as clumsy. They're very similar to each other, but they are exactly opposite.
So that lowest priority for the examples that we've been using, this hydrogen, we're saying it's low priority, and it is, but it actually makes the crucial difference between the two.
100%.
Because it is
The
the
position-
defining character between front and back.
Yes. And I have intentionally been saying low priority instead of hydrogen Because it doesn't need to be a hydrogen. It often is a hydrogen.
So it's the lowest priority, but you could argue it makes a really big difference.
It does make the biggest difference. The position of the lowest priority makes as much of a difference as describing where your palm is when you're trying to distinguish your two hands from each other. So we talked about enantiomers are non-superimposable mirror images. I think you guys would agree that if I pulled these over, the chlorines do not superimpose. They go opposite directions. And I could try to flip it, but it's actually going to look exactly the same. They're never going to superimpose. So I can see I've gone from wedged to dashed and dashed to wedged. I can physically see that the stereochemistry is different, but I can also prove that the stereochemistry is different by using our conangled tree-log rules. What about diastereomers then? Best way to identify diastereomers is to look for two things. That's why I like this connection to dia. Two things. They have at least one chiral center flipped and at least one chiral center conserved. Now, when I say flipped and conserved, I'm not saying that you are physically taking a molecule in the lab and physically changing the orientation of its bonds. What I mean is that when you're analyzing molecules on paper, you can look at how the configurations are drawn. Or if you do have molecules in lab and you're doing instrumental tests on them, this is what you look for. So could we draw a diastereomer for this dichlorocyclopentane? We could. In fact, they share the same diastereomer. They both have just one diastereomer. Their diastereomer, I think you guys would agree that both of those compounds up there are considered trans 1,2-dichlorocyclopentane. They're both considered trans, which means trans is a relative configuration. One of them is 1R, 2R. The other is 1S, 2S. That is their absolute configuration. And they both have this diastereomer, cis 1,2-dichloro. No matter which way you look at it, do you know what? Sorry, we alphabetize them. 1R, 2S. No matter how you look at it, this molecule is a 1R, 2S structure. And you can see that means 2R becomes 2S, or 1S becomes 1R. One chiral center has flipped. One chiral center has been conserved.
So would both of them being dashed be exactly the same? Or does it have to?
Yep. If both of these were dashed, I think you'd agree, Aaron, I could get there by just scooping this and flipping it like a pancake. My wedged groups, after it flips, are going to be dashed groups. So if they were both dashed, it would be the same molecule. Not another diastereomer. Okay? There's some reactions we do this semester where the products formed are enantiomers of each other. And other products that form will be diastereomers of each other. So this is a molecule that we'll look at being able to synthesize towards the end of the semester. We'll do a reaction with the starting material, and we'll form those products. What is the relationship between those products? diastereomers. The chiral center connected to the methyl group conserves its absolute configuration. The methyl group stays wedged. The chiral centers connected to the alcohols flip configuration. They go from both wedged to both dashed. Conserved, flipped. Two things have happened. Diastereomers have formed. I want you guys to actually practice saying that word, so repeat it after me. Diastereomers.
Diastereomers.
There you go. You emphasize that dia, that two-part relationship. Can't miss it. All right. We've got another thing to move on to. So any questions here on relationships between these molecules and how the absolute configuration can show you their relationship. Okay. Now we're going to take this idea of chirality, a lack of symmetry, and we're going to apply it to our molecules. There are three labels that we'll use. Two main labels. Chiral molecules. They have at least, no, that's the wrong sign. They have at least one chiral center, and they have 0 planes of symmetry. Well, that's the definition of being chiral, is lacking symmetry. There's another fun characteristic of chiral molecules. They have enantiomers. Sometimes they have diastereomers. Not all chiral molecules have diastereomers, because some chiral molecules only have one chiral center, and to have a diastereomer, you need to have two things change. One chiral center stays the same and one changes. Then we have achiral at large, which is, this has at least one plane of symmetry. And then there's a subclass of achiral molecules. If your molecule is strictly achiral, then that molecule has 0 chiral centers. It has 0 diastereomers, 0 enantiomers. Achiral molecules don't have enantiomers or diastereomers. But underneath achiral is meso. I'm not sure what meso means. If anybody finds out. What? I think that's with an I, that meso. Meso compounds have at least, you know, I've been saying greater than, but I mean to be saying greater than or equal to. Greater than or equal to at least 2 chiral centers.
Meso means middle.
Middle. Oh, so kind of like mezzanine, maybe.
Mesoamerica.
Okay. Oh, maybe it's pronounced meso and not meso. You know what? I've talked with a lot of chemists, and I've never heard anybody say meso. So
It could be Mesoamerica.
it's a dialect. They have at least 2 chiral centers. They have at least 1 plane of symmetry. So you see the relationship. A meso compound kind of cuts the middle ground between a chiral and an achiral compound. But which category would meso fit in better? Chiral or achiral? Well, I already did my little arrow. It only fits in achiral because it has a plane of symmetry. Having chiral centers is not what makes a molecule chiral. Lacking a plane of symmetry is what makes a molecule achiral, and meso compounds have a plane of symmetry. And then the fun thing about this is that they have no enantiomers because they are imposable. They are superimposable with their mirror image. So their mirror image is itself. They are identical to their mirror image. They do have diastereomers, at least 2, 1 from each chiral center flipping. They have at least 2 diastereomers, whereas some chiral molecules have diastereomers, but not all chiral molecules have diastereomers. There's a somewhat useful equation. The number of stereoisomers that a molecule can have is equal to 2 to the n, where n equals chiral centers. Actually, I'm going to refer to this as stereocenters, which is a bit more accurate. A compound that has 1 stereocenter, 1 chiral center, has 2 stereoisomers, enantiomers of each other. 2 stereocenters, 2 stereocenters, 4 stereoisomers. Unless there's a meso form. And so this is the annoying part. -1 for each meso compound. And we're not going to get too much into the math, but it is useful. So if you're looking at a molecule and you identify how many chiral centers are there, now you can go in and start figuring out how many total ways can that molecule take up space. Most amino acids have 1 chiral center, which means that there are 2 stereoisomer forms. And yet, all amino acids that are necessary for life have the same absolute configuration. So when you look at a strand of protein, which is amino acid linked to amino acid linked to amino acid, and you get maybe 50 amino acids making up 1 protein molecule, you've got now at least 50 stereocenters. So the possibilities of how many stereoisomers are there is crazy large, 2 to the 50th. And yet, you'll only find 1 stereoisomer for that protein in your body. It's fun, trust me.
Can you define stereocenters again?
A chiral center is a stereocenter, stereo meaning spatial,
Okay.
and a chiral center describes how it takes up space. So stereocenter means something that affects how it takes up space. We're actually going to learn that alkenes are also stereocenters, some alkenes.
So it's not a chiral center, but it
That's
could be a
right.
chiral center.
All chiral centers are stereocenters, but not all stereocenters are chiral carbons. Some stereocenters are other types of groups.
But a chiral center is always a carbon, right?
No, actually, no. Nitrogens can be chiral, especially like even nitrogens that have a lone pair on top, and then 3 different groups that are bonded to them. But nitrogens also have this weird thing where their lone pair can go from sitting on top of the nitrogen to kind of flipping and sitting underneath, which essentially inverts the chirality. So nitrogens can be stereocenters in biological chemistry, but they
have a formal charge.
even without a formal charge. Definitely if they did have 4 different groups and they had a positive charge, but even without, we're not going to get into it. There's also terms like prochiral, and so like a prochiral center is one that can become chiral. There's things like diastereotopic relationships where 2 hydrogens on an achiral carbon, swapping either one of them with a halogen would make it a chiral carbon, means that those 2 hydrogens are not identical. They're not diastereomers, but they are diastereotopic. Swapping a hydrogen would create a stereocenter. That describes their relationship. There's a lot of terminology. It's a bit beyond the depth of this course, so we're not going to get into it too much. I want to do some more practice with you guys here. I want you guys to have the opportunity to find, oh, I erased the wrong thing. I want you guys to take the opportunity to find compounds that are meso, chiral, and achiral. Another one I want to try. You guys are starting to see some more value in these modeling kits, right? You can start building a structure, build its mirror image, and see if they can be superimposed or not.
Wait, so sorry, for each of those you want us to
Describe its chirality. There were 2 big topics here, which was molecular relationships that's things like cis-trans isomers, structural isomers, enantiomers, diastereomers, and then molecular descriptors. You need 2 molecules to have a molecular relationship. But every molecule has a molecular descriptor. So that's things like chiral, achiral, meso, even down to chiral center, achiral center. So identify these as chiral compounds, achiral compounds, or meso compounds.
work too hard. Oh, I guess use that when you do your unit test stuff. But don't worry too hard when you get onto the exam. Can't be a perfect.
I freak out. I can't finish this.
Looking good so far. Yeah. Maybe. Does that maybe throw you off? Maybe. So not this and not this. There's literally one carbon that you haven't marked. Good start. Don't feel like you need to go through these in any certain order. Maybe. Actually, no. No, it won't be. All right, we're running out of time, so I want to get through these with you guys.
Which ones come the easiest to you? The first one came easy? What did your gut tell you?
Chiral.
Oh.
No.
No plane symmetry.
There is no plane of symmetry. If I tried to put a plane of symmetry here, the left-hand side of the molecule does not reflect to the right. So where's the chiral center then? A chiral molecule must have a chiral center. The carbon to the oxygen is achiral. It's only bonded to 3 groups. Carbon to the right of the carbonyl. That's a chiral center. It's got H, methyl, isopropyl, ketone. 4 very different groups, right? And we could prioritize them too. First priority is the carbon bonded to oxygen. Second priority is the tertiary carbon. Third priority is the primary carbon. Fourth priority is the hydrogen. I cannot tell you whether it's R or S, but it is a chiral molecule. This one? Achiral. There is that stereochemistry drawn, but it's not a chiral center, it's a tetrahedral center, but there's a plane of symmetry right here through the molecule. Cuts through that carbon. That must be a symmetric carbon. This one? Meso. Because it has 2 chiral centers, and those chiral centers are symmetric to one another. The 2 chiral centers reflect in. So it creates an achiral molecule that has chiral centers, meso compound. To the right, at the top. Chiral. How many chiral centers? 2 chiral centers. Underneath it? Chiral. How many chiral centers? Same 2 chiral centers. What's their relationship? These 2 molecules? I meant to draw diastereomers. I meant to keep the methyl group the same and change the position of the chlorine. But these, because I changed both stereocenters, these are enantiomers. Both chiral centers have flipped. And on the bottom, this one got you guys. That was meant to be the trickiest. This one is not achiral. It might be meso, it might be chiral. There are two chiral centers, but I actually do not have enough information. If they're both wedged, meso, or both dashed, meso. But if one is wedged and one is dashed, chiral. So this is either meso or chiral. There's no way to know. And I'll just clarify for you guys.
What about the plane of symmetry?
Yeah, I'll clarify that for you by sketching this out. There is a plane of symmetry if both groups are wedged or dashed. Then there's a plane of symmetry, and that makes it meso. But if one group is wedged and one group is dashed, there is no plane of symmetry, and that group is chiral. Is this the lowest energy conformation for this molecule? Do you notice how it's a zig-zag rather than a zigzag? Zigzag is the lowest energy. This is not the lowest energy, but it's a useful conformation because it shows me whether there's symmetry or not. The real lowest energy conformation here, I rotate this carbon on the right, and one of my groups looks dashed. I rotate this carbon on the right, and my dashed chlorine now looks wedged. Meso. Hard to tell from this conformation. Chiral. Hard to tell from this conformation. But there is no plane of symmetry here. My lines are going in different directions. The zigzag doesn't allow for a plane of symmetry there. There is a plane of symmetry here, but I can't see it in this conformation. Oh man, it all just came full circle.
Is it because of the dashed chlorine?
It's actually because your bond lines are going in opposite directions. You try to cut a plane of symmetry, your bond line, your zigzag, won't reflect.
Yeah.
You know? But you rotate it into a different conformation, and now your bond lines will reflect, and your chiral centers will reflect. Here, rotate it into a high energy conformation, your chlorines do not reflect. Here, your methyl groups do not reflect.
But it's because of the dashed chlorine that you're able to do that.
Because of that you can rotate it. Yeah, so you've got a dashed chlorine, and after you rotate it, it becomes a wedged chlorine.
Do you have to test all the conformations to know if it's a...
Yes and no. I would say most of the time you can get away by just finding one conformation, and it's usually pretty obvious. And this is going to become a common pattern that we'll see, just like this one rotation that makes the groups symmetric. There was one topic we didn't get to today. I don't believe it's on your unit test. I'm going to look to make sure that it doesn't pop up. But it actually is a good way to segue from this unit into the next unit next week. So there might be some reading and homework problems that you guys have seen on optical activity. We'll come back to that next week after your unit test, and we'll use it as a segue. Okay? I'm sorry for taking you guys over. Thank you for your time. Good luck on your unit test this weekend, and I'll see you guys next week.